Okay, in this video we'll be talking about related rates. Okay, and these related rates problems are certain types of problems that involve two rates, okay? Hence the name related rates, okay? Usually we're given one rate and we need to find another rate. And usually these two are related with an equation. And the equation usually has usually looks like this, where we have two rates of change with respect to time, and then we have some other variables that are usually the connected to the derivatives. Okay, so this would be an example of a differential equation. This is called a differential equation, and if we can get to this type of relationship, if we can create this kind of relationship, then we can find our desired rate given our one rate. Okay, so usually we're given information such as one rate, one variable at a certain point in time, and maybe another variable like v. Okay, depending on the situation, and then we're asked to find the a specific rate of change at a specific time. Okay. Most of the time we will be finding these differential equations by using implicit differentiation. So you might need to review how to do implicit differentiation a little bit before you do this. But we'll do that in this video as well, okay? So let's get started right away with an example, okay? It says a 5-meter ladder rests against a wall. The feet, okay, on the ground slip. So we have a ladder here. We're looking at it from the side, okay, and the feet are on a very slippery surface here, and they're slipping, okay. So it wasn't set up properly, and the ladder is sliding this way, and so you'd expect this side to keep sliding down on as it slides down this wall, okay. And at the same time, when they are 3 meters, or sorry, and at the time when the feet of the ladder are 3 meters from the wall. So when this x value is 3 meters away from the wall, they are moving at 10 meters per second. So we're given how fast this ladder, this bottom point is moving away from the wall when x is 3. Okay, and then we're asked to find at what speed is the other end of the ladder moving. So how fast is this point moving down? Okay? And so in this situation, I've already defined the variables for you, but most of the time you would not be given this picture, and you would be asked to find the derivatives, or sorry, the variables on your own. But since this is the first example, I'll go ahead and show you how to do this, okay? All right. So I would want to draw a picture first and try to understand what's happening. Then I would probably identify my variables and my constants. In this case, I have two variables. I have a height and a horizontal distance, the distance away from the wall that the feet are. And then I also have a fixed length of the ladder, which is 5 meters. Okay. So the question says, what is the speed of the other end of the ladder, which would be this, okay? So really what they're asking for is, how fast is the rate, or how fast is y changing with respect to time, okay? And all of these problems that we'll be doing, they will be the rates that we talk about here will all be differentiated with respect to time, okay? And so we're going to assume that x and y are both functions of time. We can define where the position of the height, where the position of this point will be with respect to time, and this we can describe where this point will be with respect to time. Okay, so these are really functions of time. So at the point x equals 3, we know that dx is 10 meters per second, and at this point, the question is, what's y? And what's dy dt really. This is my goal here, okay? So we need to find a relationship first between x and y. Okay, so that's always our goal. We want to connect this variable and this variable, and then we can find the connection between the rates of those using implicit differentiation. So let's first find the relationship between x and y. By Pythagoras' theorem, we're going to find x squared plus y squared is 5 squared. And since we know x is 3, we can now solve for y. So when x is 3, y will be 4. Okay, so this is a specific situation here. Now don't plug this back in, okay? Don't plug this back in just yet. What we need to do is we need to come back, we need to find a derivative relationship. We need to find a relationship between these derivatives. And since I don't have any derivatives right now, since all I have is this right here, I need to use implicit differentiation, okay? So I'm going to implicitly differentiate, okay? And what that will do for me is that will provide for me these terms, dx dt and dy dt, right? Oops, sorry. So let's differentiate here. I have this relationship. I'm going to derive that implicitly. That means take the derivative of this side, take the derivative of this side, okay? So this becomes, now we're deriving with respect to time here, okay? So keep that in mind. We're always doing these problems with respect to time. So this becomes 2x times dx dt, and that's because of the chain rule, right? That's really just the chain rule. And again, I'm going to emphasize with respect to time here, okay? Plus 2y dt, and this side, the derivative of a constant is 0. And so we end up with this relationship. And this relationship then is my differential equation. Okay? Once I get this is probably the hardest step. Once I find this, then I can now start substituting my numbers in, my given information. Okay? So now let's go back. And the question was, when x is 3, what are all the other conditions? So I'm given this, I'm given this, I found this at this time, right? And now we're asked to find dy dt. So I just substitute those in. So I do 2 times 3 times 10 plus 2 times 4 times this, which is still a variable, and that's what I want, equal to 0. So I solve this equation, I simplify, that becomes 60, that becomes 8 times dy dt, and 8 dy dt is negative 60. I divide both sides by 8. I end up with dy dt equals negative 7.5. And our units are going to be in meters per second, right? Meters per second. So to answer the question, when the rate of change of x is 10 meters per second, the rate of change of y is going to be 7.5 meters per second. Okay, so let's kind of recap. Okay, so let's just kind of recap what steps we took. First, we drew this diagram, right? Then we found a relationship between all of the variables. We labeled our variables. We labeled the constants. We found the relationship. We found the differential equation from that relationship, and then we plugged in our numbers. Okay, so that's kind of the procedure that we're going to take. If you want to write down your notes here, this is a step-by-step way of doing this procedure for this. We drew a picture of a diagram. We labeled the diagram, distinguishing between variables and constants. We connected the variables with an equation. Okay, and oftentimes we do this with Pythagoras' theorem, using our knowledge of similar triangles, right-angled triangle trig, okay, using our trig functions, and sine and cosine rules. Okay, these are very common relationships that we use to find the equations. Differentiate after you get your equation, differentiate with respect to time, and since all of our variables here should be functions of time, okay, we're going to assume that most of the time, we can use implicit differentiation there. And then we evaluate to find the unknown rate, which is what we were asked to find in the first place. Okay, so in the next couple of videos, we'll go over some more examples of related rates problems.